Yeah. Okay, so sorry, I forgot to turn on the recording at the very beginning. You can go back over the slides. I think so far we haven't done anything too terribly complicated, but the rest will be recorded for you. I apologize, I forgot to turn the recording on. Okay, so what is this degrees of freedom? Why do we divide by n minus 1 instead of n? Well, basically, the number of independent variables that we used in order to determine the standard deviation is not really n. It's actually one less than that, because the first measurement that you make, you could use that to make an estimate of the average value, but you don't know anything about the standard deviation until you measure at least 2 values. Then you know how far apart are they, right? What's the expected error in this measurement? So that's basically where this comes from, that we divide by n minus 1 instead of n. Okay, so let's look at an example. So a student takes independent repeated measurements of the atmospheric pressure in the laboratory during their physical chemistry lab period. The student records values that are given here, expressed in units of torr. So calculate the mean and the standard deviation of the data. Okay, so the mean, x bar, that's going to be just 762.2 plus 762.0 plus 761.8 plus 761.5 plus 62.2 plus 760.0. Okay, so we sum all the numbers up that we measured, and then we divide by the number of measurements, which in this case is 6. Okay, and so this average then is, if you punch that into your calculator, you're going to get 761.62 torr. Okay, and we'll just leave this rounded to 2 decimal places for now. When you go to write your lab report, you're going to want to use the correct number of significant figures, which we'll talk about a little bit later. Question or no? Okay. Okay, good. So that's the average. So what about the standard deviation? Sigma for these measurements? Well, sigma is just the square root of 1 divided by the degrees of freedom, which in our case is, we took 6 measurements. So the degrees of freedom that we would use in this calculation is 5. Yep. And we're then going to take the sum over each measurement, and we're going to take the difference between the measured value, so 762.2, and the average. So subtract 761.62. And then we do this for each point. So 762.0 minus 761.62 plus, oh, I'm sorry, and we square each one. 761.8 minus 761.2, square that. Okay, keep going. 761.5 minus the average 761.62 squared plus 762.2 minus 761.62 quantity squared plus 760.0 minus 761.62 quantity squared. Okay, and I'll close my squiggly bracket parentheses here. And if you punch this all into your calculator, you should get a standard deviation of 0.835 torr. Okay, but this is, as you can see, it's a little bit cumbersome to write out this formula and to punch these numbers individually into a calculator. So what you can also do is you can use a computer to make your life easier. And so we're going to also do it this way using a spreadsheet. So let me stop my share from my tablet and then go over to my laptop and share my screen. Let's see, which one do I want to share? I'll just go to share desktop 1. that should work. Oh, whoops, no, don't want to do that. Share. Okay, hopefully this works. Okay, so I think you should be able to see, yeah, this presentation now, or this, sorry, this slide, or this, sorry, spreadsheet now. Okay, is that big enough to see all the numbers? I'll make it a little bit bigger. Okay, I'll do some deleting before we get started. So we'll pretend that this didn't have all this already solved for us. Okay, so you took some measurements of the pressure and you entered them into a spreadsheet. And a spreadsheet is just basically a table. In Excel, if you use Excel, the columns are labeled with letters, the rows are labeled with numbers, and you just enter the values that you measured here. And you can then use built-in formulas that will allow you to make calculations much faster than doing them out by hand. So what you use to write a formula is you start a formula with an equal sign. And the built-in formula for the sum is just called sum. And if we want to take the sum of all these numbers in order to calculate the average, then we just select the range of the range of data that we want to sum over, and close the parentheses, hit enter, and we get the sum. Okay, in order to calculate the average, we just take the sum. So I'm going to say equals, and then C8. I could either type C8 or click on C8 and then divide by the number of measurements, which is 6. Okay, so we get an average of 761.62. That's exactly what we got by doing it the long way. We can also calculate explicitly the standard deviation using the formulas. So first, we can calculate the deviation of each value from the average. And so for this first value, the deviation is just going to be the measured value minus the average value. But I'm going to do a little trick, which is to put a $sign in front of the cell reference, in front of the letter C and the number 10, that's referencing the average value. And what that does is it makes it an absolute reference rather than a relative reference. And what that does is if I grab the bottom right corner of this cell and drag it down, then it copies the formula, but it changes the value of this first cell reference because I didn't put $signs there. So when I drag it down, it changes C2 to C3. So this number then is C3 minus C10. This number is going to be C4 minus C10 and so forth. So I get all of the deviations, right, of each measured value. We then need to square those in order to calculate the standard deviation. So here I'm just going to take this number and square it. And again, I can use the click and drag trick. And there's all the deviations squared of each measurement. And the standard deviation then is given by the square root. That's just SQRT of the sum of the deviations. So actually, before I do that, let me sum up all of these deviations here. So sum of all these numbers. Okay, and then here I want the square root of this number divided by the degrees of freedom, which in this case is 5. Okay, we actually could have done this even quicker using other built-in functions that are available in Excel. So we could have just used the average function, which is denoted average. So I could have just written equals average and then click on the range of values that I want to take the average of. And as you can see, we get exactly the same number. Okay, we could have also done this with the standard deviation. The built-in function for standard deviation is called stdev. And I'm going to enter in the range of values. And again, we get exactly the same thing that we got calculating the long way. Okay. And if you do calculations using a spreadsheet or using some other software program that you want to use, it's nice to provide your TA with a little annotation, which just shows which which formulas you used to calculate different values. So if you're going to print this out and turn it in, please provide just a little annotation like this one shown here so that your TAs can see what you did. Okay, I'm going to now go back to my presentation, I think. So first I will go to Zoom. Where's the meeting? Maybe I need to, here we go. Stop share. Okay, I'll start the share again from over here. Okay, so now I'll go back to this presentation. Okay, oops. How do I get rid of this? Okay, now it looks correct. Okay, so let's keep going. Okay, so if you take a bunch of repeated measurements of a number, you know, like sort of like we've encountered in the past example, usually you get you know, a bunch of results that are sort of centered around the expected value that you're trying to measure, but they might be, you know, each point is located a certain distance away from that value. So if you took a repeated measurement of some quantity X, you know, and you get the following measurements, you could plot those on a number line. And you could sort of look at, you know, you could eyeball this and, you know, it kind of looks like these different measurements. They're centered around an average value of something like 200. And then the standard deviation that we learned how to calculate, this is basically a characteristic value that says on average, how far would you expect a measurement to be located away from this value 200? So if we just sort of look by eye, well, you know, most of the values are sort of between, I don't know, 170 and 225 or so. So maybe the standard deviation is something like 20 or 25. Okay, but for many types of problems in physics and physical chemistry, the distribution of values that we measure is described by what's called a Gaussian distribution. And a Gaussian distribution is a function. It looks like this. It's also called a bell curve or a normal curve. The formula is given by this equation here. So basically you have an exponential, and in the argument of the exponential, you have the value of a given measurement, x, minus the average value of x squared divided by 2 sigma squared. And this sigma here is basically the standard deviation associated with the measurement that we talked about on the previous slide. Okay, and the x bar would be the average of many measurements. If you took an infinite number of measurements, you'd be able to measure this value of x bar and this value of sigma. And the sigma, the standard deviation, also enters in the prefactor here. Okay, and the way that a Gaussian distribution is defined is such that the probability of observing a measurement within a finite interval between A and B is the integral from A to B of this Gaussian function that describes the probability distribution. Okay, that's how it's defined. So, you know, let's say that we had a probability distribution described by this function here. It's going to have there's going to be a very high probability, let's say, of finding a measurement that's between, say, 190 and 210, where you're at the center of the distribution. Then there would be of finding a measurement that's between like 140 and 160, right? Because the area under the curve in this region is less than under the curve near the center. Okay, if you make a measurement, you're guaranteed to get some number between negative infinity and infinity. And so therefore the probability of measuring some number between negative infinity and infinity has to equal 1, which is another way of saying the curve is normalized. Okay, if you change this value x bar, then you shift the center of the Gaussian. So for example, if you change x bar from 0 to -2, then you would go from this blue function to this green function. And if you increase the value of sigma, then you increase the width of the Gaussian. So sigma is a measurement of how broad the distribution is, or in other words, what the spread is in the characteristic spread in the data points that you measure, what that's going to be. Okay, and any Gaussian function that's properly normalized has the following property. If you take the integral of a Gaussian function between the average minus sigma and the average plus sigma, so plus or minus 1 standard deviation, you're going to get a value of 0.683, which means that there's a 68% probability that any given measurement will fall within 1 standard deviation of the mean. Okay, but we don't have to take this integral with just 1 standard deviation. We could also take this integral shown here and vary the number of standard deviations that we integrate. And so if you set t in this equation equal to 2 and integrate, then you would get a value of 0.954. So basically what that means is that there's a 95% chance that a given measurement is going to fall within 2 standard deviations of the mean. Or if you set t equal to 3, you're going to get an integral of 0.997. So there's a 99.7% chance that a given measurement will fall within 3 standard deviations of the mean. So it becomes, as you increase this number t, the probability becomes really high. And so what that means is that there's only a 0.003% chance, or I'm sorry, a 0.003 probability, fractional probability of finding a measurement that's more than 3 standard deviations away from the mean. Okay, you could also take this equation and set p of t equal to exactly 0.95 and solve for t numerically. And as you can see from this table, it's going to be approximately 2, but not exactly 2. And in fact, if you solve for t, you're going to get exactly 1.96. So there's exactly a 95% probability of finding a measurement within 1.96 standard deviations of the mean. That's what this means. And so this relationship has an important name. The interval from plus 1.96 standard deviations of the mean to minus 1.96 standard deviations away from the mean is called the 95% confidence interval, or the 95% confidence limits. And we can express that as delta 95. Delta 95 is 1.96 times the standard deviation. Okay, so that's where you would expect 95% of all the measurements to lie, within that interval. Any questions so far? Okay, if not, let's move on. Okay, so we've talked about the standard deviation for individual measurements. Each individual measurement is expected to, disagree with the average measurement by approximately plus or minus a standard deviation, something like that. But what if you take a set of n measurements and determine the average? So let's say you come to lab one day, you take a set of n measurements, you calculate an average and a standard deviation from that first data set. And then you come to lab again the next day, and you take another set of n measurements, and you again calculate the average and the standard deviation. And if you do the measurement the same way, you would expect to get numbers that are similar from day to day, but not exactly the same, because you have random error that's associated with the measurements that you're taking. And so if you perform this process many times, and then ask yourself, well, what's the standard deviation of this mean value that I obtained from n measurements, right? In other words, how much fluctuation will there be from day to day? If I take like 10 measurements every day, then that quantity is called the standard deviation of the mean. And it is denoted sigma sub m. And statistically, you can show that this is equal to sigma divided by the square root of n. And so, so what would you expect? If you have one student who comes to lab and makes 20 measurements every day and takes the average of those measurements and then reports their average from one day to the next. And if you have another student who's maybe not quite so diligent and only takes 5 measurements each day and then reports the average each day, which set of averages would you expect to have a larger standard deviation? The student who took more measurements or less measurements? Yeah, if you take fewer measurements, you would expect that the error is not going to average away as well. And so you're going to have more fluctuation from day to day. And that's basically what the square root of n tells you in the denominator. The more measurements you take, the smaller the standard deviation of the mean is going to be. But there's this really pesky square root sign in the denominator. And as a result of this square root, the standard deviation converges to 0 in a way that is really, really slow, unfortunately. So it's not practical to just average ad infinitum to make your standard deviation of the mean go to 0, because you sort of run up against a limit where it's not practical to keep on taking measurements anymore. And so, for example, if you want to increase or if you want to decrease the confidence limit by a factor of 10, right? If you want to get 10 times more precise value, you would have to take 100 times as many measurements, right? So, you know, let's say a set of measurements took you 3 hours to do in lab. If you wanted to get a result that was 10 times more precise, you would have to spend 300 hours measuring, which most of you probably don't want to do. So there is a limit to how much advantage you can get from averaging. Okay, so if you take a set of n measurements and take the average, then another important thing to ask is, well, what would be the 95% confidence limit for the average of n measurements? And the answer is, well, this is the 95% confidence interval for an average, right? So it's called 95% confidence limit of the mean. And this formula is valid for if n is a large number. And this is just 1.96 times the standard deviation divided by the square root of the number of measurements. Okay, but most of the time in the lab, we only take a finite number of measurements. And if you have a relatively small sample set, you actually cannot use this formula. You would instead, if you're sort of in the limit where, you know, n is between like 2 and 20, then you need to use what's called a student t factor, which is denoted t of nu sub 95. And basically, you can look these values up in a table. And in this case, you're going to use this formula to compute the 95% confidence interval. So the 95% confidence interval for a limited, if you have a limited set of data, you look up the 95% confidence interval student t factor from a table, multiply by the standard deviation, and divide by the square root of the number of measurements. Okay, this nu here, this is the number of degrees of freedom. And for the mean, nu equals n minus 1. Okay, and this is really important because for most of the measurements that you take, if you take repeated measurements and report the uncertainty, this is the number that you want to report. Right? You can be 95% confident that the real value lies somewhere in this interval. The probability of the real value lying outside of this interval is only 5% statistically. Okay, any questions? Okay, so here's an example of a table of student t factors. So the student t factor that you use depends on the number of degrees of freedom. This is the number of measurements minus 1. For if you're reporting the uncertainty in a average. So if nu is 1, you have to multiply by 12.7 to get the 95% confidence interval. But if you take more measurements, right, if you have a larger number of degrees of freedom, then this value decreases because your uncertainty decreases the more measurements you take. Okay, so I think next we're going to do an example. So we're going to calculate the standard deviation of the mean and the 95% confidence limit for the data in example 1. Okay, and so how do we do this? Well, I'm not going to go back, but you can look back at the numbers if you want. So in example 1, the mean value of the pressure that we obtained was, let's see, it was 761.62 torr. And the standard deviation that we obtained was 0.835 torr. Okay, so what is the, and there were 6 measurements. So what is the, going to be the standard deviation of the mean and the 95% confidence limit? Well, the standard deviation of the mean from our formula is just sigma divided by the square root of the number of measurements. So that's going to be 0.835, sorry, 835 torr divided by the square root of 6. And if you calculate what that's equal to, it's 0.341 torr. And the 95% confidence interval then, delta 95, is just going to be, well, we need to take the student t factor, and the number of degrees of freedom is 5. So I'm going to set nu equal to 5 here. And then times sigma. I can either multiply by sigma m, or I can multiply by sigma divided by square root of n. And so what's this T95 value going to be? Well, we have to look that up in the table. So nu equals 5. So the student T factor that we're going to use is 2.57. Okay, so this is equal to 2.57 times sigma, which was 0.83. Pen isn't writing very well. 835 torr. Oops. Divide by square root of 6. And this is going to come out to 0.876 torr. Okay. Okay, so if you made this measurement and you wanted to present the results, how would you actually present it when you go to write a report? Well, there are various ways that you're going to see numbers with uncertainties presented. One way is to use this parentheses notation, which basically means the number that's given. So you present a number and then you give a number in parentheses. And this number in parentheses here represents how much uncertainty there is in the last printed digit of the value. So this notation here, 3.42 parentheses 4 bar, means 3.42 bar, but with an uncertainty of 4 in this last digit, which is a digit of 2 in the hundredths place. So basically that means that the uncertainty is 0.04. What if it's greater than 2 degrees of magnitude? What if it's greater if this number here was like a 2-digit number? Sometimes you will see that. And then basically it would, so if this number here were like a 12, that would actually mean 3.42 plus or minus 0.12. But for the purposes of this course, we're going to round all the uncertainties to 1 digit. So you wouldn't do that. You would just write 3.4 parentheses 1 in that case. Does that make sense? Okay. Another way that's a little bit easier to understand is to write uncertainties with plus or minus. This is what I recommend using. And so in terms of the 95% confidence limit, delta 95, writing the uncertainty with a plus minus, let's say you made a measurement of the heat capacity of a certain substance and you get 66.32 joules per Kelvin with a 95% confidence limit of 0.21 joules per Kelvin. So in this course, what we're going to do is we are going to round the uncertainty to 1 digit, which means we would round in this case, the first digit that's non-zero is this digit in the 10th place here. So we're going to round it to the nearest 10th of a joule per Kelvin. So the uncertainty that we're going to report is 0.2 joules per Kelvin. And then whichever digit has this uncertainty, that is the last digit that you want to report in the value that you're reporting. So we're going to round the value that we measured to the 10th place and report it as just 66.3. plus or minus 0.2 joules per Kelvin. Okay. What if the value has, some order of magnitude that's very different than 1? Maybe you would want to report a number that's like, 0.5 microvolts, and you would report that as 5.02 times 10 to the minus 4 volts. And maybe it has an uncertainty of 0.5 millivolts, and it has an uncertainty of 5 microvolts, so 5 times 10 to the minus 6 volts. Then a convenient way to write it is to convert the uncertainty so that it has the same exponent as the value that you calculate. So 0.05 times 10 to the minus 4 is the same as 5 times 10 to the minus 6. And then you can put both the value and the uncertainty in parentheses and multiply by 10 to the minus 4. Okay. If you want to be really explicit, you can also write in parentheses that this is the 95% confidence limit, and you can report the number of measurements. So you would report that by just writing 95%, comma, n equals 7 in parentheses. Okay. Sometimes in high precision measurements, you will see uncertainties reported with more than 1 digit. But for the purposes of Chemistry 3108, you can just round everything to 1 digit of uncertainty. Okay. Let me check the time. How are we doing? Okay. It's 10 till 7. So we can keep going a little bit. Okay, so the next example problem, we're going to represent the numerical results that we obtained in example 1, right? This repeated measurement of the laboratory pressure with the 95% confidence limit and the mean. Okay, so the value that we calculated for the mean was 761.62 torr. And the 95% confidence limit that we calculated was 0.876 torr. Okay, and when we did the initial calculations, we just left the rounding the way it is here. I calculated extra digits more than I needed to avoid round off errors. But when we actually go to report this number, we're going to round the uncertainty to 1 significant figure, 1 digit. So it's going to be 0.9. And the uncertainty then is in the 10th place. So we're going to round also the average to the nearest 10th of a torr. So we would report this number then as 761.6 torr plus or minus, plus or minus 0.9 torr. And do remember, when you're reporting your final answer, always include the units. Otherwise, your answer doesn't mean anything. Okay, and if we wanted to be really explicit, we could also write this is the 95% confidence interval, and it was obtained with n equals 6. Okay, so this would be a final result that you could report in your lab report if you made this measurement. Okay, the next topic that we want to discuss a little bit is rejection of outliers. And okay, so I'll introduce this with an example. So let's say you're measuring, you're doing a chemical kinetics experiment. You're measuring the rate of a chemical reaction. And you get the following values from repeated measurements in units of reciprocal second. So you get 3.8, 3.5, 3.9, 3.4, and then 1.8. So one of these values is not like the other. So this value of 1.8 looks like it's not really matching with the other values. And so you might ask yourself, should I include this or not include this when I analyze my results and calculate the average? So that's the question that we're gonna be asking is this outlier statistically outside the range where we would expect to be able to find it? And so in order to answer this question, what we're going to want to do is we want to calculate how many standard deviations away from the mean is this outlier that we calculate, or I'm sorry, that we measured. So we can calculate based on all of the data that we took what is the average value and what is the standard deviation. So if you did that, you'd get 3.4 and 0.8. And then you can calculate this quantity T out, which says how many standard deviations is this outlier away from the mean. And so you just calculate, you take the value of the outlier minus the average, right? This is how far away you are from the mean, and divide by the standard deviation. And that's this T value that you're going to use. So in our case, this would be 1.8 minus 3.4 divided by 0.8, which is equal to 2. So basically, this outlier is 2 standard deviations away from the mean of the set of measurements. Okay, and as we as we saw from our previous discussion of the Gaussian distribution, 2 standard deviations corresponds to approximately the 95% confidence interval. So there's about a 5% chance that a number would or that a measurement would fall more than 2 standard deviations away from the mean. So that would correspond to 1 out of about every 20 measurements. So is it reasonable that you would get this number 1.8 in a certain set of measurements? Well, the answer depends on how many measurements you took. So if you took 20 measurements, statistically you would expect at least one of them, right? There's a 5% chance that at least one of them is going to fall outside of the plus or minus 2 sigma limit. So if you took 20 measurements, it might be reasonable to have one such outlier. But let's say you only took 5 measurements, like we did in this case, then it would be unlikely to have this event occur, which only has a 5% probability of occurring. Okay, so in this case, maybe this number is unreasonable. Another way to think about this is, if you take 20 measurements, then you could have an outlier, and it's not going to affect your average very much because you have 19 other numbers that were close to the center that you're averaging together with. But if you only take a small number of measurements, then an outlier is going to have a larger effect on the mean. It might skew your result more. Okay, so the criterion then that you can use to determine whether to get rid of the outlier is called Chauvinist Criterion. And basically, the criterion is such that if you take the number of measurements times the probability of having a measurement be more than T out standard deviations away from the mean, if this expression here on the left side of this inequality is less than 0.5, then we say that this outlier would be improbable to have in a set of n measurements, and we should reject the outlier. That's basically how this criterion works. Okay, so I'm not going to derive exactly how you would determine this, but there's an easy sort of cookbook method that you can use, and we'll go through that. So you're going to calculate the average value of the measurements and the standard deviation. You're then going to go to a table. So this is table C1 of your lab manual. By the way, chapter 1 of your lab manual contains all the information that we're going over in these lectures. So if you want to look over it in more detail, you can either look through these slides or you can read chapter 1 in the lab manual. But you're going to look at table C1 in the lab manual, and C1 has a value of T max for a particular number of measurements, right? That's the number of standard deviations away from the mean that you're allowed to be and still be within the criteria of Chauvinist criterion. And if this T out is more standard deviations away from the mean than T max, then you're going to reject the outlier. And you would then recalculate the average and the standard deviation using the remaining n-1 measurements. Okay, and here's the table that you can use. So here's the, in this column, you have the number of measurements. And in this column, you have the value of T out, which is the, basically how many standard deviations are you away from the mean. Okay, so in the next example, we're going to apply Chauvinist criterion to determine the outlier in the data in example 1, and see whether or not we should reject that outlier. Okay, so in example 1, let's see. I'll just go back and show you the numbers. Oops, sorry. Okay, so here are the numbers that you measured. It might be a little bit less obvious, but one of these is an outlier, or seems to be an outlier. Which one? Yeah, exactly, 760.0. So basically all the values here are somewhere between 761.5 basically and 762.5, except for this value. It's a little bit lower than the other ones. Okay, so we're gonna determine whether that is an outlier or not, statistically. Okay, and so the way that we can do that is, so the average that we got for these values was 761.62 torr, and the standard deviation was 0.835 torr. And the maximum number of standard deviations that were allowed to be away from that average value, we look that up in a table. So T max, we go to our, oops, sorry. Okay, here we go. So the number of measurements in this case was 6. And so T out is going to be 1.73. So this is the value that we're going to use. So T max equals 1.73. And then how many standard deviations away from the mean was this outlier? Well, that's just the value of the outlier minus the average value, divide by the standard deviation. So for our example, that was 760. Oops, 760.0, that's the value of the outlier, minus the mean is 761.62. Take the absolute value, divide by sigma, which is 0.835. And the numerator and denominator both have units of torr, so the T out is unitless and it's 1.94. Okay, and so this is further more standard deviations away from the mean than T max. And so the conclusion is we should reject the outlier. And we should recalculate the mean and the standard deviation without that point. And so if we do that, I'm not gonna do that by hand because it's too much work, but there is a spreadsheet that's on the Blackboard site that you can use. And I'll show it to you. So basically, where did this go? Chauvinist, here we go. Okay, so you should all be able to see the spreadsheet now. Okay, so we calculated the average and the standard deviation of these measurements. For 6 measurements, T max from Chauvinist Criterion is 1.73. We can calculate based on this table or based on these numbers, the value of T for the outlier. So that's going to equal just the absolute value of the outlier, which is 760, minus the average value, which was 761.6166, and then divide by the standard deviation. Oops, sorry. Divide by the standard deviation, enter. Okay, and we get 1.93. That's exactly what we got when we did it by hand. And so T out is greater than T max, yes. And so we remove the outlier. So we're gonna ignore this value 760, and we're gonna recalculate the average and standard deviation without that number. And then we could take the average of just the first 5 values and the standard deviation of just the first 5 values that we measured. So we're gonna select from here to here. Okay, and now you can see, so the average increased a bit relative to what it was before. That makes sense because this outlier was lower than the other values, so it was skewing the result low. And the other thing you can see is the standard deviation decreased rather significantly, which is also what you would expect to happen if you remove an outlier. Okay, I'm going to go back to the presentation. Okay, so that was the first section. I'll try to get through the second section today. If we don't quite make it, that's fine. We can pick up where we left off next time. The next section is about error propagation. And so the cartoon says, I didn't know how to propagate my error correctly, so I just put error bars on all my error bars. Okay, but you're not going to have this problem because you're going to know how to propagate error correctly. Okay. Yeah. Thank you for pointing that out. Yeah, so the question is basically, if you had two data points that are outliers, what would you do? And the answer is, to make sure you do it correctly, the best way to do it is take the outlier that is the furthest away from the mean and apply Chauvinist's test to that outlier. If that outlier should be rejected, then you're going to reject that outlier. And then using the remaining data set, you would iteratively repeat Chauvinist's criterion again on the remaining data points, and you would take the next furthest away outlier. Is that clear? So basically, you're going to apply it to one point at a time, but iteratively. Okay, so often you do an experiment where you might be measuring two different values, and then you have to calculate some other value as a function of these two measured values, both of which have uncertainty. So maybe you have a measured value of x, and you would express that as x best plus or minus delta x, and you have a measured value of y, which you can express as y best plus or minus delta y. And if you assume that the uncertainties are independent and random, that is, they're not due to systematic error, but due to random error, then there are ways to propagate the error if you're taking some function of these two measured values, x and y. And if you take a sum or a difference between x and y, that is, if you're trying to calculate some value q, and it's equal to the sum of x and y, or the difference of x and y, then the best value of q is just the average value of x plus or minus the average value of y. And the uncertainties have to, however, be added in quadrature, that's just a fancy way of saying that you use this formula to calculate the uncertainty in this value q. And this formula, the way you can remember it is it looks a lot like the Pythagorean formula for determining the hypotenuse of a triangle with legs of length delta x and delta y. But you just take the square of delta x plus the square of delta y, and then you take the square root of the whole thing. Okay. And so that's if you have a sum or a difference between two measured values. That's how you would treat the error of the sum or difference. But what about if you want to take the product of two numbers that are measured, or the quotient of two numbers that have an uncertainty associated with them? Then basically the fractional uncertainty ends up getting added in quadrature. So if you take the uncertainty in q, if q is equal to xy or x over y, then delta q divided by q, right? So the relative uncertainty in delta q is equal to the relative uncertainty in delta x squared plus the relative uncertainty in delta y squared. Okay? There are some special cases that you can consider. What if you have a number that has an uncertainty associated with it, and you add or subtract an exact number? So like, for example, what if you measured an angle and it has a certain uncertainty, and you want to know what is the complement of that angle? Well, that would just be 90 degrees minus the angle that you measured. But 90 degrees is an exact number. That's just the definition of complement. So adding or subtracting an exact number does not affect the absolute uncertainty, the absolute error, right? So in this case, delta q is equal to delta x. Okay, what if you multiply by an exact number? What if you measure the length of one of the sides of a square, and then you want to know what's the perimeter? Well, the perimeter is just 4 times the length of the side, right? But 4 is an exact number. It doesn't have an uncertainty associated with it. But if there's if your measurement X is off, then the error is just going to add up when you add the different sides. So the uncertainty then in n times X is going to be the absolute value of n times the uncertainty in X. Okay, another formula you can use is this one. If you have a number to the power of an exact number where X has uncertainty, n is an exact number, then the relative uncertainty in the result is equal to absolute value of n times delta X over X. Okay. Okay, so that's sort of what you would do if you are adding together numbers or taking products and quotients of numbers. But what if you have a more complicated function, right? So let's say you have a function and it looks like this. So Q is some function of X. Well, you might expect, based on what you know from calculus, that the uncertainty in Q is going to be related to the slope of this function. So if this function is changing really quickly with respect to X, right? If dq dx is large, then if you have a small uncertainty in X, that could lead to a large uncertainty in Q. Whereas if the slope of this function is not so much, right? So if you're in this region over here, then the same change in X, right? The same uncertainty in X would lead to a smaller change in Q. And so in fact, so what is going to be the uncertainty in Q then? Well, you could sort of estimate that by taking Q of X best plus delta X minus Q best. Or using calculus, you could say that Q of X plus U, where U is some small change in X, well, that's just equal to Q of X plus the derivative of Q with respect to X times this small interval, right? This U is equal to your delta X, basically. And if the quantity is measured with an uncertainty delta X, and it's used to calculate the function Q of X, then the uncertainty in Q is just going to be the absolute value of the derivative evaluated at X best times the uncertainty in X. Okay, so I think we are just about out of time. We have a few more minutes. But yeah, it's probably not enough time to do this whole example. So why don't we stop here for today? I'll finish this section next time, and then we'll start talking about fitting regressions. So using linear and nonlinear regressions to determine parameters. Okay, any questions before we leave for today? Okay, I don't see any. If you have a question, feel free to email me or stick around after the meeting. And I will see everybody on Thursday.